In this stage, we're going to see how encoders work and how to use them to make a cheap trick autonomous to make your robot stop after a certain distance. Encoders are special devices that are used to measure the rate at which something rotates and how far it has rotated. Normally, you'll see encoders used on robot drivetrains to give their users a general idea, sometimes a fairly accurate idea, of how far the robot has traveled. This is particularly useful in autonomous because a lot of times, if you have to shoot something, if you have to move to a particular position or a certain amount of feet, it's kind of good to know how far you've actually gone and where you need to continue moving to. The way encoders work is a little strange. They are technically digital input devices, and they use digital inputs in order to work, but they're kind of special. The encoders that we will normally use small rotating discs that have slits in them, and light is shined through the slits, and a sensor on the inside of the encoder counts the number of slits that it sees go by. Using this information and a little bit of math, you can figure out how far and how fast your robot is moving. As I mentioned in the previous videos, this video will include code from previous videos, continuing to build upon what we've already written. We've added quite a bit more stuff to this video, so we've got quite a bit to talk about. As with before, we have all the same stuff that we had before. Speed controller objects for our drivetrain motors, speed controller groups for the two sides of our drivetrain, differential drives, so we can control everything together, an Xbox controller, so we actually have something to control with, a bumper button to stop our robot if we bump into something, and a potentiometer to control our speed as we're moving. And then, of course, we have our potentiometer range variable, which came from before. Now, the next two things that we create is a left side encoder and a right side encoder. We have an encoder on each side of our robot. I did this because sometimes it's better to average the two sides if you're trying to go in a straight line. There's also other code that you can use called pathfinding code that can actually use two encoders independently of each other to turn the robot to a particular location. There was one thing that Ethan and I were experimenting with last year that should be included in this year's libraries called JC's Pathfinder library. Pathfinder? I can't quite remember. I think it's Pathfinder. That can be used for just that. And it's actually really cool in how it does it. And hopefully it will be included in this year's code so that more teams can make interesting and effective autonomous codes. Oh boy. Okay. We'll see how we create the left encoder and right encoder objects in a second. I want to talk about the three new constants that I created. The first one just defines how many inches we want to travel in autonomous. In this case, I set it to 60. 60 is just a good number. It was 5 feet. I mean, I've got the space in the garage to move that far, so that's what I picked. Wheel circumference and linear dist per step work in tandem with each other. We need to talk a little bit about this. So the way I have my encoder set up on my robot is they share the same connection with my wheels on my robot. That means that they're in a one-to-one relationship. For every one revolution of one of my wheels, my encoder has rotated once as well. So what I need to do is calculate how many inches I travel when one tick of my encoder happens. If you remember, I talked about the light shining through the little slits. One light shining through is a tick. The way we do that is by relating rotational travel with linear travel. Now, generally speaking, when a wheel rotates, the amount that the wheel rotates, the distance of the outside of the wheel that rotates, is the same as the linear distance traveled, how far you actually moved. So if a wheel is 6 inches around and the wheel rotates one time, you've more or less gone 6 inches. There is a little bit of leeway for flex of the wheel and that sort of thing, but generally speaking, it doesn't affect the math enough on our end to cause any problems, so we don't generally factor it in. So the way we figure this out is the first thing we need to do is figure out my wheel's circumference. Now, the way we do that is by multiplying pi by the diameter of my wheel, which just so happens to be 6 inches. So that is the wheel circumference. So we have that information. Now what we need to do is we need to find out the linear distance per step. Linear dist per step. Basically linear distance per tick, one of those little slits in the encoder. My encoders are configured so that there are 512 of those little slits for one revolution. Normally you can find this information on the encoder's data sheet. A data sheet is basically just a description of how a sensor works, how an electronic component works. The encoders that we use a lot on drivetrains are called AMT 103Vs. They're pretty popular because they came in the kit of parts for a couple of years and teams have just sort of stuck with them. They're made by CUI Inc. and they're really nice, really rugged encoders. And they're fairly easy to use. They actually have little digital switches, digital inputs on the inside of them that allow you to change how many ticks, how many little slits the encoder will detect per revolution. In my case, I set mine to 512. I believe the default is 256, but I set mine to 512 just for a little bit more accuracy. The way we find the linear distance per step is literally by dividing the circumference of the wheel by however many number of ticks there are in a revolution of the encoder. So in this case, we take the wheel circumference divided by 512. Now that we have that information, we can actually go down and create our encoders. Now, if you remember, digital input 0 is taken up by our bumper button. So we start using other digital inputs in order to create our encoders. I have no idea why this is here. It shouldn't be. So I'm going to remove this. Forget that was even there. I don't know why it was there. Maybe I do. Let's put it back and we'll talk about it. This is why you need to put comments in your code. I think I have comments in some of my other code for this, but I didn't put it in here. But anyways, what we do is when we create an encoder, we have to specify 2 digital inputs, at least for something called quadrature encoders, which is what the AMT 103Vs are. We won't get into the difference between quadrature encoders and other types of encoders. Just know that you need to have at least an A channel and a B channel for a quadrature encoder. So in this instance, for the left side encoder, we have digital input 1 and digital input 2 on the DIO rail. We also use the set distance per pulse, effectively set distance per tick, and we set it to that linear distance per step that we calculated above for our constant value. We then do something similar with the right encoder. We specify that we want to use digital inputs 3 and 4, and then we also specify the distance per pulse, the distance per tick. Now, the right encoder has something else called on it called set reverse direction. Basically, all this does is it tells the encoder that when it is counting, forward means backward, and backward means forward. It basically just inverts values like what the not sign would do for a Boolean value. I don't quite remember why I had to do this. Maybe something about how I set my encoder up was backwards. Maybe I plugged something in backwards. That's entirely possible. I haven't looked at it since. I will need to go back and look before I run the test. Maybe something is configured. Yeah, I think something's configured backwards. Anyways, not really important. And generally speaking, you may or may not have to use set reverse direction. If you see numbers coming in the wrong way when you're working with your encoders, set reverse direction is a really fast way of changing that number. Now we move on to robot periodic. We talked about this a couple of times in 2 previous videos. Robot periodic being the method that gets called roughly every 20 milliseconds while your robot is running in any mode. In the previous videos, we specified bumper button pressed and pot angle to send to our smart dashboard. In this video, we're also adding data from the left encoder and the right encoder. Now, the put data method is used with something called sendable objects. There are a handful of sendable objects that can be sent to the smart dashboard, and encoders are just one of them. We'll see gyroscopes in the next video. Gyroscopes are another object like left encoder and right encoder that we can send to the smart dashboard by using the put data method. Put data basically just makes it so you don't have to individually grab things like the speed that the encoder is reporting, the distance that the encoder is reporting, the distance per tick that each encoder is reporting. It's basically just a fast way of putting a lot of data on the smart dashboard all at once. And all you have to do is give it a name, like anything else, and then specify a value. In this case, we're specifying the left encoder and the right encoder, respectively, for each value. Now, if you remember in previous videos, we didn't have anything in the autonomous init method. In this case, we have 2 things. A reset call for both the left encoder and the right encoder. Basically, all this does is it resets the encoder to 0. It specifies 0 distance, it specifies 0 speed, it sets everything to 0. The next thing that we do is we tweak our autonomous periodic method a little bit. Now, we're going to add something to the if statement in order to be able to tell whether or not we've gone the amount of inches that we want to travel in autonomous. Now, what I do is I end up averaging the two encoders on each side of the drivetrain. So get distance will always return a value in the units that you specify when you set the distance per tick, the distance per pulse. In this case, we set the value in inches. If you wanted to set the value in parsecs, as long as the resolution of a double is enough to set it in parsecs, when I say resolution, I mean the number of decimal places, the number of digits after the decimal place. You could do that if you wanted to. It'd be a little bit asinine, but you could do it. In this case, get distance for both the left encoder and the right encoder return inches. What we do is we simply add them together, divide them by 2, and save them to a new variable that I call distance traveled average. Then what we do is we modify our if statement a little bit and say if the bumper button is pressed and the distance that we've traveled so far is less than the total distance that we want to travel, the auto distance in inches, which was 60, then what we want to do is we want to drive forward based on the value currently specified by the potentiometer. We talked about this math in a previous video. Basically all it says is give me a value between 0 and 0.5. 0 and half speed for the robot. Now, if either the bumper button is pressed or the distance traveled is greater than or equal to the auto distance that we want to travel, we're going to stop. This is one of those ways where you can make it so that if the button is pressed too early and you want your robot to keep moving, then as long as the button gets unpressed at some point, the robot will continue to move until it makes it the certain number of inches that you specified in that constant that we made above. That being said, this is a really crude way of using an encoder. And in fact, we'll be able to see later in other videos different ways of reading sensor values so that your robot can react to changes in the environment more dynamically. So, like, let's say your robot needs to be exactly at 60 inches and it travels 65 inches. There's other code that you can use to make your robot automatically drive backwards after driving forwards in order to correct for that extra 5 inches that you travel. That's in a future video. It's called PID control. We'll talk about it more when we get to that point. But basically, this is all that's changed. Teleop periodic is still the same. Autonomous periodics got a little bit more complicated. Now, that being said, this was, of course, a very fast rendition of encoders. We didn't talk about getting the speed, although speed is not necessarily always as important. There are some things where speed can be useful, like measuring the speed of a shooter. So if you have any questions, obviously, Facebook, text message, phone call, email message, whatever works for you, however you need to get a hold of me, friend of a friend, whatever works, please ask your questions. I'm trying to get all these videos done before my surgery coming up, which is 2 weeks before kickoff. But if you send me a message, if you try to get a hold of me, I will respond as soon as I can. That being said, the next thing you'll see in this video is a demonstration of how this code works. And in the next video, we'll see how we can add a gyroscope into the mix.